Good morning, all of you. Welcome to Sri Jayendra Rank Zone. So far, we have completed 17th group and 18th group. Now, we are going to discuss D and F block elements. This chapter is very, very important. It is coming under inorganic chemistry study. So, we are starting now D block elements, D and F block elements. From this chapter, also, you may expect questions for entrance examinations, and it's very easy also. So, please listen carefully. Now, we are going to start D and F block elements. So far, we have completed P block elements, that is 15th, 16th, 17th, and 18th group elements. Now we are going to start D block elements. So let us start now. Introduction. D block elements are defined as the elements in which the differentiating electron enters into n-1. Differentiating electron means the valence electron. What is the differentiating electron? Means the valence electron, that is the last electron. Valence electron enters n-1 d subshell of penultimate shell. N-1 d subshell of penultimate. Penultimate means outermost shell. Before that, whatever is there, that is called penultimate shell. The shell before outermost shell is called penultimate shell. And till now, we have seen valence electron entering into p subshell. Now here the valence electron is entering into n-1 d subshell of penultimate shell, and it is not going to last shell, it is going to penultimate shell. That is most important. So the D block of the periodic table contains the elements of the groups 3 to 12. Groups 3, group 4, group 5, group 6, group 7, group 8, group 9, group 10, and group 11 and 12. So the elements constituting the F block are those in which the 4F and 5F subshells of anti-penultimate shell. This is anti-penultimate shell, means before the penultimate shell. So that is valence shell, penultimate shell, then anti-penultimate shell. So F block elements are nothing but in which the differentiating electrons enter into the F subshell, 4F and 5F subshells of anti-penultimate shell are progressively filled. So this is nothing but D and F block elements. So what are D block elements? The elements in which the valence electron or differentiating electron enters n-1 d subshell of penultimate shell is called D block elements. And the elements in which differentiating electron enters into the n-2, here we can say here n-2 F subshell, n-2 F subshell, and that is 4F and 5F subshells of anti-penultimate shell. Here it is anti-penultimate shell are progressively filled. So these are called F block elements. These are called F block elements. So what is D block? What is F block? We have explained. Just note down. Next, series of transition elements. We have total 4 series in transition elements, that is 3D, 4D, 5D, and 6D series. So there are many 3 series of the transition metals, but actually fourth series is also there, but that is incomplete. That's why we have 3 series. That is 3D series, 4D, 5D, and 6D. So 3D series starts with 3D 1 to 10, 4S 1R2. 4D series 4D 1 to 10, 5S 1R2. That is 3D series, that is scandium to zinc. Scandium to zinc, that is atomic number 21 to 30. The elements with atomic number 21 to 30 are called as 3D series elements, and they are all metals. Most important point is all the D block elements are metals. There is no non-metal in D block elements. All the D block elements are metals. All the D block elements are metals. And first D block series is 3D series. It starts from scandium and ends with zinc. Scandium atomic number is 21 and zinc atomic number is 30. And the configuration is 3D 1 to 10, 4S 1R2. And 4D series, 4D 1 to 10, 5S 1R2. That is yttrium to cadmium. Y means yttrium. Yttrium to cadmium. CD means cadmium. That is constituting 4D series elements. Total it is 10 elements. And 5D series elements, we have 5D 1 to 10, 6S 1 and 2, lanthanum to mercury. Lanthanum, La means lanthanum, and Hg means mercury. And 60 series is 60 1 to 10, 7s 1 or 2, actinium, and it is incomplete. And it is incomplete. So each series consisting of 10 elements each. Very important to note down. Each series consisting of 10 elements each. And all the elements in D block are metals. 10 elements each series. So every series consisting of 10 elements each. So these are the elements of D block: scandium to zinc, yttrium to cadmium, lanthanum to mercury, actinium to incomplete, because still the elements are being discovered. So that's why you can say it is incomplete. Next continuation. Series of inner transition elements, that is F block elements. These are also called D block elements are called transition elements, and F block elements are called as inner transition elements. F block elements are called as inner transition elements because they form F series. That's why they are called as inner transition elements. These are placed separately in the periodic table. These elements are placed separately in the periodic table, as we have noticed. There are two series of inner transition elements. One is lanthanides and the is actinides. Lanthanides forms 4F series and actinides forms 5F series. The configuration is lanthanides is cerium to lutetium. Ce means cerium. Cerium to lutetium. And thorium to lawrencium. Th means thorium, atomic number 90, and lawrencium, atomic number, that is Lr, symbol is Lr. So atomic number is 103. And these two series consisting of, each series consisting of 14 elements each, 14 elements, 14 elements each, and in total, how many F block elements we have? 28 elements. Total 28 elements are there. 28 elements are present in F block elements. So 14 elements each, and in total it is 28 elements because this is 14 and this is also 14. So these are called lanthanides and actinides. It starts with lanthanum, but still lanthanum is D block element. It starts with actinium, but still actinium is D block element. So since they have properties related to lanthanides and actinides, that's why these series are called as lanthanides and actinides. Even though lanthanum and actinium belonging to D block elements, but they have placed here because they have similar properties with that of 4F series and 5F series. So that's why they have placed here. So inner transition element starts with cerium to lutetium and thorium to lawrencium. These are the elements of 4F series and 5F series. Next continuation. What are transition elements? A transition element is defined as the one which has incompletely filled d orbitals. It has incompletely filled d orbitals in its ground state or in any one of its oxidation states. So they have incompletely filled d orbitals. Zinc, cadmium, mercury. These have completely filled d orbitals of group 12b, have fulfilled D10 configuration in their ground state as well as in their common oxidation states, and hence these are not considered as transition elements, transition metals, but still they are placed in D block elements because of some similarities. What are the elements which are not transition elements but still included in transition elements? Zinc, cadmium, and mercury. This type of question you may expect in entrance question. So which of the following is not a transition metal? Zinc, cadmium, and mercury. These are the elements which are not transition metals. Why these are not considered as transition metals? Because what are transition metals? A transition element is defined as the one which has incompletely filled d orbitals, but these have zinc, cadmium, and mercury. If you see zinc atomic number 30, atomic number 30. So it has configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2. So it has completely filled d orbitals. Total 30, 12, 18, 20, 26, 28, 30. So this is total 30 elements. So zinc, even you find the same thing in cadmium as well as in mercury also. So zinc, cadmium, mercury, as they contain fully filled d orbitals, fully filled, are completely filled d orbitals. That's why they are not considered as transition elements, because what is a transition element? It is defined as the one which has incompletely filled d orbitals, as it contains incompletely filled d orbitals in its ground state or in any one of its oxygen states. They are called as transition elements. But zinc, cadmium, and mercury, in their ground state only, they have fulfilled D10 configuration in their ground state as well as in their common oxidation states. Hence, what is the common oxidation state of zinc? Zinc will form Zn plus 2, means 2 electrons from 4s will be removed. So, as completely filled electrons in D10. So, that's why they are not considered as transition metals. They are not considered as transition metals. Continuation. So, please note down in your classwork. All the slides are important. General properties of transition elements. Now we are going to discuss general properties of transition elements and trends in general properties. Electronic configuration. Each member of transition metal has n-1 d1 to 10 ns1 to 1 or 2 electron ns1 to 2 electrons configuration as the outermost general electronic configuration. So the general outermost electronic configuration is of d block elements total, it is n-1 d1 to 10 ns1 to 2, where n is called principal quantum number. The electronic configuration of 3D series elements are given below. You can just see here 3D series. If you see, then you can follow the same thing for 4D also. So scandium, it has argon 3d1 4s2. So n-1, n-1 here, n is equal to 4. So n is equal to 4 means n-1 becomes 3. So 3d1 4s2, 3d1 4s2 electrons in the s orbital. Titanium 3d2 4s2, vanadium 3d3 4s2. Argon is the common, that is 18th element. 18 electrons are present in argon, as we already know. So 3d5 4s1, 3d5, the filling of electrons will be like this. You have to notice this. In d electrons, in d orbitals, how the electrons are filled based on Hund's rule. So no two electrons will pair up. So based on Pauli's exclusion principle and Hund's rule and Aufbau principle, they fill accordingly. So first electron, second electron, third electron, fourth electron, fifth electron. After filling 5 electrons in the 3D subshell, sixth electron will fill, then sixth electron will start pairing up. So first 5 electrons will not paired, only sixth electron is pairing up. Seventh, then eighth, then ninth, then 10th. So all the electrons are paired up. So in this way, and copper, this is ground state configuration for copper. It is exceptional because it is 3d10 4s1, 3d10 4s1. Why? Because as it is completing all the electrons in d orbital. So that's why it will take, rather than 3d9 4s2, instead of 3d9 4s2, instead of 3d9 4s2, copper will take 3d10 4s1. Similarly for chromium also, it is exceptional configuration, that is 3d5 4s1. Here only one electron in s orbital, here also only one electron in s orbital. These two are exceptional cases. Why? Because half filled and completely filled orbitals are more stable than incompletely filled orbitals. So half filled orbital, that is 3d5, and completely filled orbital 3d10 are more stable than, for this actually it should come 3d4 4s2, 3d4 4s2, but instead of this it is going like this, 3d5 4s1. So chromium and copper are important in this configuration. Remaining all, it will follow according to the Aufbau principle. So this is 3d1 4s2, 3d2 4s2, 3d3 4s2. 3d4 4s2 we don't have, 3d5 4s1, 3d5 4s2, 3d6 4s2. So manganese is also having unusual stability because all the 5 electrons are filled and 2 electrons are filled in s orbital. So it is half filled d orbital and completely filled s orbital. So that's why manganese is also having unusual stability. Iron, cobalt, nickel, copper, zinc. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. These are the filling of electrons, and these are the 3D series. These are the elements of 3D series. And very important point, all are metals, but they are less electropositive than first group and second group metals. These are less electropositive when compared to first group and second group metals, that is S block elements. Continuation. atomic and ionic radius. In the same period, order of atomic radii and ionic radii, S is greater than D is greater than P, as we already know. First S block, then D block, then P block. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. These are the elements of 3D series. That is third group 2. Actually, we should see across because they are not considered as groups because they have completed D elements, transition elements. And scandium atomic radius is 162, 147, 134. So as we move from left to right, as we move from left to right, that is as we go down the group, simply you can say go down the group. As we go down the group, the atomic radii decreases. The atomic radii decreases and sudden increase in case of zinc, it is been happening. So atomic radius decreases, radius remains constant in between because 126, 125, 124, they are very close and atomic radius increases at the last. So atomic radius depends on effective nuclear charge. Very, very important point is the atomic radii will not follow general trend. Atomic radii depends on effective nuclear charge Z and screening effect Xe. So in dipositive ion of 3D series, copper plus 2 is the smallest one. Copper is having smallest atomic radius. In dipositive ion means copper on losing 2 electrons becomes Cu plus 2. So this is the atomic radii trend. So it is not following a regular trend. So listen carefully. So why it is increasing here? Because of Poor shielding effect. Here poor shielding effect taking place and here screening effect is less. That's why it is increasing. Let us discuss that. The atomic radii and ionic radii of the elements of 4D series are higher than that of 3D series. Very important point. So the atomic radius of 4D series are greater than 3D series due to increasing number of shells because that is going to a 3D subshell and this is going to 4D subshell. But the elements of 4D series and 5D series have almost equal radii due to lanthanide contraction. Very, very important. What is lanthanide contraction? So in third group of order, in the 3B group, order of atomic radii is scandium less than yttrium less than lanthanum to lutetium. So when compared to the atomic radius of 3D and 4D, 4D is having greater atomic radii than 3D series elements. But in between 4D and 5D, they have almost equal radii due to lanthanide contraction. What is lanthanide contraction? Due to poor shielding effect of d electrons. Poor shielding effect means due to poor shielding effect of due to poor shielding of d electrons. The outer electrons will come closer to the nucleus. The outer electrons, the outer electrons will be under nuclear attraction, will be under nuclear attraction, nucleus attraction, sorry, it is nucleus attraction. So due to which what happens, the outer electrons will be under nucleus attraction. So hence atomic radii will not decreases. Atomic radii decreases because they will come close to the nucleus, due to which contraction takes place. That's why it is called lanthanide contraction. Contraction means size will decrease, so atomic radius decreases. So why it is decreasing? Why the atomic radius of 4D series and 5D series are comparable? They have almost equal radius because of lanthanide contraction due to poor shielding of d electrons. The outer electrons will be under nucleus attraction, so atomic radii decreases. So note down this statement in your classwork. So continuation now. So this is the trend of atomic radius. Third group based on green line. Green line is scandium to zinc. So atomic radius decreases down the group from scandium to zinc because for scandium it is more. Next it is titanium. Next it is vanadium. Next it is chromium. Next manganese, iron, cobalt, nickel, copper, and zinc. For zinc it is increasing. When compared to copper, atomic radius of zinc is more. That is most important. So this line is most important. When compared to copper, copper atomic radius is less than zinc. So first it decreases, then it remains stable, then again it increasing. Next for 4D and 5D series, if you see 4D is yttrium to cadmium. The atomic radius decreases gradually like this. The atomic radius decreases gradually, and finally it is increasing up to cadmium due to completely filled electrons. In zinc and cadmium, due to completely filled electrons, shielding effect is less. So due to which what happens? They have more atomic radius than their predecessor element. That is predecessor element is silver. Silver is having less atomic radius than cadmium. Silver is having less atomic radius than cadmium in the second series. Silver is having less atomic radius than cadmium. Similarly, for gold and mercury also, you can see here gold and mercury. Gold is having less atomic radius than cadmium, sorry, mercury. But if you notice the atomic radius of 4D and 5D, they are almost equal because of lanthanide contraction due to lanthanide contraction 4F series and 4D series and 5D series, they have almost similar radius. So what are the elements that have similar atomic radius? That is zirconium, hafnium, zirconium, hafnium, zirconium and hafnium. If you see, they are similar. This is zirconium and hafnium. So zirconium and hafnium, this also they will ask due to lanthanide contraction. The atomic radius of which elements are equal, almost equal, that is zirconium and hafnium. Zirconium and hafnium. And you can see niobium and thallium. So niobium and tantalum. This is tantalum. And this is, what is this called? Third one, molybdenum and tungsten. Molybdenum and tungsten. So almost they have similar, but these two are extremely close. These two are extremely close. So that's why we can say it is nothing but zirconium and hafnium have similar atomic radius in 4D series and 5D series due to lanthanide contraction. So this is the effect of lanthanide contraction. What is lanthanide contraction? This is not configuration. I just wrote wrong. You can please check it out. So this is called lanthanide contraction. Lanthanide contraction. So due to lanthanide contraction, these two are similar. What are these two? Zirconium and hafnium are almost similar. It is equal to, actually we can say. So remaining they are very close to each other. This is just approaching 14.2, 14.6 like that. So just small difference, slight difference, but these two are extremely equal. These two are extremely equal. And down the group, the atomic radius decreases first, and finally it increases due to completely filled electrons in zinc, cadmium, and mercury. So why finally it is increasing? Because due to completely filled d orbitals. Due to completely filled d orbitals in zinc, cadmium, and mercury, they have more atomic radius than the previous, that is the previous element in that particular group. This is very, very important graph. You can understand it easily. Down the group, the atomic radii first decreases, becomes stable at the middle, and finally it is increasing due to zinc, cadmium, mercury have completely filled d orbitals. So that's why the atomic radius increases. Shielding effect decreases for these three. For which element shielding effect decreases in 4D, 3D series and 5D series? That is zinc, cadmium, and mercury. Due to less shielding effect for these elements, shielding effect is less. So that's why lanthanide contraction will have no effect on these elements. So that's why it is increasing. So please note down all these points clearly. What I have mentioned, what I have rounded up, you can just see. When compared to atomic radius of 3D, 4D is having more because 3D atomic radius is up to 13, least is 13, but it starts with more than 15. So, so 3D atomic radius is greater than first element. You can see 16 plus. So 3D and 4D having, sorry, 4D and 5D series elements have more atomic radius than 3D elements because it is total, it is 16 and it is starting with 17. This is 17.2, something like that. That is radius in nanometer. So this is the trend of atomic and ionic radii of 3D, 4D, and 5D series. 6D is incomplete, that's why we are not discussing it. Next continuation. Lanthanide contraction. What is lanthanide contraction? This is observed usually in 4F series and 3D series. In 4f series, the electrons are added to the 4f subshell. Due to the ineffective shielding of these 4f electrons, the effective nuclear charge increases from left to right in 4f series. As a result of this, there is a regular decrease in the atomic size of elements of 4f series from left to right. This decrease in atomic size is known as lanthanide contraction. As I told you, as the outer electrons are coming under nuclear attraction due to effective nuclear charge, due to which what happens, the size of the atom decreases. That is, the decrease in atomic size takes place. This is called as lanthanide contraction in 4f series, and even it can observe in D series also. That is 4D and 5D series. In 3D will not it will not applicable, but 4D and 5D series. I'll write it clearly. Not only 4F series, it is also applicable in 4D and 5D series. This lanthanide contraction, but it is less when compared to F series. In F series, lanthanide contraction is more when compared to D series. So in 4D, 5D, and 4F series and 5F series, the electrons are added to 4F subshell. So here the electrons are added to 4D subshell and 5D subshell. Due to ineffective shielding of these 4F electrons, like 4D and 5D electrons, the effective nuclear charge increases from left to right in 4F series. As a result of this, there is a regular decrease in the atomic size of elements of 4F series from left to right. This decrease in atomic size is known as lanthanide contraction. This is called lanthanide contraction. So please note down. Next continuation. Due to this lanthanide contraction, they'll ask what is the effect of lanthanide contraction in the examination, entrance exams. Due to this lanthanide contraction, the 5D series elements, very, very important, please note it down. The 5D series elements will have similar, less atomic size than expected, and they have almost same size of that of 4D series elements in the same group, as we have seen in the graph. So 4D and 5D series 180, 187. Very small difference. Zirconium and hafnium. These two are almost same as I told you. This is 160 picometers and this is 159 picometers. And niobium, niobium and tantalum also the same. That is 146 and 146. And molybdenum and tungsten also the same. That is 139, 139. So due to the lanthanide contraction, this lanthanide contraction, 5D series elements will have less atomic size than expected, and they have almost same size as that of 4D series elements in the group. So which elements are similar due to lanthanide contraction in D series? Zirconium, hafnium, niobium, tantalum, molybdenum, and tungsten. Molybdenum and tungsten. So these are the elements which have similar atomic size, even though they are placed in 4D as well as 5D series due to lanthanide contraction. These two are little bit, yttrium and lanthanum, still slight difference is there, but these are very close to each other, and these are given in picometers. And when compared to 3D, automatically 4D will have more atomic radius because 3D scandium, it is 162 picometers, but this is 180. Titanium 147, but this is 160. But 4D and 5D, they have very close atomic radius values due to lanthanide contraction. This is the first effect of lanthanide contraction. Next continuation. Atomic volume and density. The atomic volume of transition elements are low. The atomic volume of transition elements are low compared with S block. The size decreases along the period, and therefore atomic volume also decreases along the period. So why it is decreasing? Because of atomic size decreases. As the atomic size decreases, atomic volume also decreases along the period. The decrease in metallic radius coupled with an increase in atomic mass results in the increase in density of these elements. So that's why osmium is the highest density element, that is 22.57 grams per centimeter cube. And iridium also 22.61. Next highest is osmium, and iridium have highest density. So which of the elements denser element? So which element is having maximum density in total periodic table? It is osmium and iridium. Iridium is having maximum density, that is 22.61, and osmium also. And one more important thing I want to tell you, that is osmium 22.57 density, highest density is osmium and iridium. But osmium will show, osmium even exhibits even +8 oxidation state. The only element which exhibits +8 oxygen state is osmium. It exhibits +8 oxygen state also, very, very important. So because of its highest density, osmium can exhibit +8 oxygen state. Iridium also the same way. Iridium and osmium can exhibit highest oxygen states, that is +8 also. So why D block elements have more density than S block elements? Because of as the atomic size decreases along the period, and therefore atomic volume increases, also decreases, sorry, atomic volume also decreases along the period. The decrease in metallic radius coupled with an increase in atomic mass results in the increase in the density of these elements. As the metallic radius is decreased with the increase in atomic mass, results in the density of these elements. So these elements are more denser than S block and P block elements. So that's why D block elements have highest density. The highest density elements are osmium and iridium in the whole periodic table. So atomic volume and density continuation in all groups except 3b, there is normal increase in density from 3d to 4d, and from 4d to 5d increase is double due to Lanthanide contraction. So the density increases due to Lanthanide contraction when compared to 4d and 5d due to Lanthanide contraction. So this is also one more effect of Lanthanide contraction. Due to Lanthanide contraction, the density of 5d elements are more, that is far more greater than 4d, as due to Lanthanide contraction. And 3d to 4d when compared normal increase in density, but from 4d to 5d we have high density. So density increases from scandium, titanium, vanadium, chromium, manganese, manganese, iron, cobalt, nickel, copper, and zinc. Density decreases. So density almost constant at the middle. So highest density in the third period is copper, lowest density is scandium, and technetium, man-made element and radioactive. So that's why it is not discussed. Technetium, TC. So please note down these points in the classwork, because any point from this they can ask in the entrance exam. So all the points are very important. So that's why we have made perfect notes for you in the form of PPTs. So please make use of these PPTs compulsorily. Next, we have metallic character. All the transition elements possess 1 or 2 electrons in the outermost shell, and these exhibit metallic nature. As I already told you, all the transition elements are metals in nature. All are hard, ductile, malleable except mercury, because mercury is liquid at room temperature. Mercury is what? Liquid at room temperature. So that's why it is less hard, ductile, and malleable. One big group element, that is copper, silver, and gold, are almost ductile, ductile and soft. These are good conductors of heat and electricity. These are good conductors of heat and electricity, that is copper, silver. Silver is the best conductor, already we know. Copper is also, that's why all the electrical components are made up of copper, because it is cheaper when compared to silver. And gold also is a good conductor of heat and electricity, but it is costlier. It is not economical. That's why we will not use gold wires, but we'll use copper wires, and silver also. So the order of conductivity, silver is the best conductor, as I already told you. But due to economy wise, copper is cheaper. So that's why we'll use maximum copper. So silver greater than copper, greater than gold, greater than aluminum. So which is the best conductor of the electricity? That is silver. But silver will not use because of its price. Next, covalent and metallic bonding both exist in the atom of transition metals. Very, very important. In transition metals, not only ionic bonding, covalent and metallic bonding will be existing, because they are less electropositive than S block elements. So they are covalent in nature, as well as they have internally metallic bonding, which is a weaker bond, easy to break up. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. The shapes of scandium, it undergoes HCP, hexagonal cubic lattice, that is BCC lattice, BCC, BCC. These are not so useful, but still, as it is given, we have to remember this, because this we have discussed in solid state also. In solid state, we have important metals. So it is forming hexagonal close packing, cubic close packing, body centered unit cell, body centered vanadium, hexagonal close packing, and BCC. So cubic close packing, cubic close packing, cubic close packing, and this is zinc, that is HCP, yttrium, zirconium, niobium, zinc, and all these are given in solid as they are metals. They are in solid state, except mercury. That's why mercury is given X. That is nothing is there. So this is CCP and HCP. Cadmium is X again, but still it is HCP because it is solid, except mercury. So remaining all they form like this. So either they form BCC or CCP. There is no simple cubic. There is no metal which is simple cubic. That you have to remember. So BCC and cubic close packing, body centered cubic close packing, and body centered cubic and face center. CCP means what? Face center, and HCP also face center. So these are the elements. So all the metals will have either body centered or cubic close packing. The cubic close packing means it can be HCP or only CCP. That is based on solids. Next, melting points and boiling points. Melting points and boiling points of D block is greater than S block because D block elements are metals and they have highest density. So they automatically they have melting points and boiling points because they are solids at room temperature. S block is this is due to strong metallic bonding as well as unpaired electrons leading for covalent bonds. As D block elements have unpaired electrons, as we have seen in D block elements, 3D series, 4D series, 5D, and 6D, they have at least one or two unpaired electrons, or three, four electrons, three, four, one, two, three, or four unpaired electrons. So that's why even five also you can take. So they have at least five unpaired electrons. Five unpaired, one, two, three, four, five, if we take. So from one to five unpaired electrons. So as they have one to five unpaired electrons, leading for covalent bonds. That's why they are covalent in nature. Zinc, cadmium, and mercury have low boiling points and melting points due to completely filled d orbitals, which do not show covalent bonding between their atoms. That's why the compounds of zinc oxide is ionic, zinc chloride is ionic, like that. So the compounds of zinc, cadmium, and mercury are predominantly ionic because, and as they have ionic, they have low melting points and boiling points due to completely filled d orbitals, which do not show covalent bonding between their atoms. But still, they have low melting points and boiling points because of completely filled d orbitals. And in a given transition series, the melting point increases on moving left to right in a period and attains a maximum value and then decreases. At the last, it decreases. So from scandium to zinc, from scandium to copper, if you take, from scandium 3D series, if you take from scandium to copper, melting point increases on moving left to right. And after copper, for zinc, it decreases. For zinc, it is decreases. Similarly, in yttrium to cadmium also, from yttrium to before the cadmium element, it decreases, it increases, melting point increases, but for cadmium, it decreases. So at the end of the elements, it decreases. At the end, maximum value attains the maximum, and then it decreases at the end. So this is a trend of melting and boiling points. All the trends are not regular. So that's why these trends are important for examination point of view, especially in entrance exams, they'll ask these trends. So please do more questions on trends of melting points, boiling points, atomic area, all the general properties. Very, very important in D block. In D block only we have general properties mainly because from general properties only we are going to get questions in the entrance exam. So all these general properties, each and every point is very, very important. You have to remember for the examination and you have to follow the trends. So this is due to the increase in the number of unpaired electrons in the beginning and reaches a maximum in the middle of the series. And again, it decreases. Tungsten has the highest melting point, that is 3653 kelvins in 3D series. So tungsten is having highest tungsten, that is in 5D series. You can say this is 3D, 4D, and 5D. So which is having highest melting point? Tungsten. And in 3D series, which is having in 4D, which is having highest melting point, that is molybdenum. Molybdenum in 4D. Here I'm writing separately. In 4D series, highest melting point is molybdenum. In 5D series, it is tungsten. Tungsten is having highest melting point in 5D. And in 3D series, chromium is having highest melting point. Chromium is having highest melting point in 3D. So these are the elements which have highest melting points in their particular periods. So in their series, that is 3D chromium, this is chromium, and 4D molybdenum, and 5D it is tungsten. And highest melting point is having tungsten, that is 3653 Kelvin. That's why it is used as filament. Due to its high melting point, it is used as filament in electric bulb so that it can withstand high temperature. It is used as tungsten is used as filaments in electric bulb. Why it is used as filament in electric bulb? Because electric bulb produces large heat energy. So to withstand that heat energy, the filament is made up of tungsten. As the filament is made up of tungsten, it will not melt so that the bulb works continuously. So tungsten has highest melting point of 3653 kelvins. 3653 kelvins is more than 2000 degrees C. So more than 3000 degrees C. That's why it is having, it is used as filament in electric bulb. So due to the increase in the number of unpaired electrons in the beginning and reaches a maximum in the middle of the series and again decreases, the melting point trends will be like this. So first it is increasing, then it starts decreasing, finally again it's decreasing again. Here also in middle it increases and again finally decreases. Here also first it increases, then it starts decreasing. So anyway, first increases, in the middle it slightly decreases and slightly increases and then again decreasing. So this is the general trend of melting points of 3D, 4D and 5D series. Next, enthalpy of atomization. So the what is enthalpy of atomization? The amount of energy required or given out to form the atom is called, the formation of an atom from the element is called enthalpy of atomization. So the enthalpy of atomization is high due to stronger interatomic attractions. The enthalpy of atomization is high for 3D series, 4D and 5D due to strong interatomic attractions. Greater the number of valence electrons, stronger is the resultant bonding and higher is the enthalpy of atomization. So more energy is required to form an atom. The members of 4D and 5D series have greater enthalpy of atomization than those of 3D series. So all these are very important. Any point they can ask in the entrance exam. The variation of enthalpy of atomization of 3D, 4D and 5D series is shown in the graph below. You can see this graph easily, you can understand. So let us see the graph. That is the enthalpy of atomization of 3D, 4D and 5D series. So 3D series is red line, 4D is blue line, series 1, 2, 3. So that is 3D is green, 4D is blue, and 5D is red. So this is, I'll write it here so that to avoid confusion. So this is 3D, this is 4D, and this is 5D. So the enthalpy of atomization is of 4D and 5D is more when compared to 3D series. This is called enthalpy of atomization. In the third series, the enthalpy of atomization of zinc is lowest. Why? Because of completely filled d orbitals. Due to completely filled d orbitals, they have lesser attraction force. Due to which, as they have more number of electrons and complete filled orbitals, they have lesser attraction force, due to which enthalpy of atomization is lowest. So in any series, the last element is having lowest enthalpy of atomization due to completely filled d orbitals. Due to completely filled d orbitals. Please note down this answer in your book. Continuation. Explain why transition elements have many irregularities in their electronic configuration. They have many irregularities in their electronic configuration because because due to first point molecular attractions, or you can say attractions and repulsions, mainly attractions and repulsions. If electrons are less, they have attraction more, and if the electrons are more, they have more repulsions because of like charge. And second point, half filled and completely filled, half filled and completely filled, completely filled. And third point, completely filled d orbitals. So it has many reasons, important reasons I'm writing here. Third point, due to lanthanide contraction. Lanthanide contraction also, we have many irregularities. Lanthanide contraction. So they have irregularities in their electron configuration, and even more important is due to variable oxidation states. Variable oxidation states, because they do not have only one valency, they have more than one valency, variable oxidation states. So all these are the four reasons. Based on this, we have many irregularities in their electronic configuration. Please copy down in your classwork. Next. The melting points of zinc, cadmium, mercury are low. Why? As we already know, they have completely filled d orbitals. They have completely filled d orbitals. Hence, their melting points and boiling points are low because they have lesser attraction. The electrons will have, the molecule atoms will have lesser attraction. That is no metallic bonding. No metallic bonding. Metallic bonding present is weaker. Low metallic bonding instead of, you'd say it's better. Low metallic bond. That's why their melting points and boiling points are low. So next, we'll continue with the topic. Continuation of this topic. More about general trends we are going to discuss now. After that, we'll do questions based on general properties. Next, we have next general property. We have ionization enthalpies. What are ionization enthalpies? The definition already we know. So the amount of energy required to remove the valence electron is called ionization enthalpy. And ionization enthalpy is purely depending on atomic radii. In each series of the transition elements, ionization enthalpy increases from left to right due to increase in the nuclear charge. That is, ionization energy value increases up to manganese and then becomes irregular due to irregular trend of atomic size and counterbalance of effective nuclear charge and screening effect. So up to manganese in 3D series, it increases. Then it starts decreasing and it is having irregularity because due to irregular trend of atomic size. As I told you, ionization enthalpy purely depending on atomic size. So due to lanthanide contraction, what happens? Ionization enthalpy first increases, then decreases, then again increases. So because ionization potential depends upon atomic size, effective nuclear charge, and screening effect. The ionization value of 5D series are higher than that of 3D and 4D series due to weak shielding effect of 4f electrons present in the 5D series elements. That is, ionization energy of zinc, cadmium, and mercury are abnormally higher on account of greater stability of S subshell. Due to greater stability of S subshell, the ionization energy of zinc, cadmium, and mercury are abnormally higher. But within the 3D, 4D, and 5D series have more higher than that of 3D and 4D because of weak shielding effect of 4f electrons. Due to poor shielding effect of 4f electrons present in the 5D series elements, the ionization potential value the initial enthalpy value is higher because the outer electrons will come closer to the nucleus. As the outer electron, that is valence electron, are coming closer to the nucleus due to effective nuclear charge, it is very difficult to remove that electron. So hence high ionization enthalpy is used. So I think it is clear. Next continuation. So the first ionization energy of first four 3D series elements are scandium, titanium, vanadium, and chromium differ only slightly, whereas the first ionization enthalpy of iron, cobalt, nickel, and copper have also fairly close to one another. Whereas for manganese, it is unexpected. It is highly more because it has more number of valence electrons. As the number of valence electrons increases, ionization potential also, that is ionization enthalpy also increases. But in case of manganese, so characteristic properties of transition elements. Next topic we have, that is first topic is variable oxidation states. Colored ions, as they have unpaired electrons, they exhibit color. As most of the transition elements have unpaired electrons, they exhibit color. And as they have unpaired electrons, even they have paramagnetic in nature. And catalytic properties, uh, most of the transition metals are used as catalyst. Why? Because they provide clean surface for adsorption. They provide clean surface for adsorption. This topic already we have discussed in surface chemistry. Why the metals are only transition metals have taken as catalyst in most of the reaction, that is iron, cobalt, nickel, platinum, etc. Because they provide clean surface for adsorption. And once the adsorption takes place, the reactants will come closer to each other, due to which what happens, the reaction takes place faster. That's why they are used as catalysts. And most of the transition metals are forms alloys, formation of interstitial compounds, and formation of complexes. So all these topics are most important. So these are the general characteristics of transition elements. What are alloys? Alloys means mixture of two or more metals in a suitable proportion. So they are called as alloys, like stainless steel. Stainless steel is an alloy. So formation of interstitial compounds. Interstitial means we have, as due to the variable valence, they form interstitial compounds. These interstitial compounds also we discuss. And formation of complex compounds also, because they have more d electrons for bonding, so that's why they form complex compounds. As they have availability of d electrons, and expanded octet availability of d electrons, they can form complexes easily. So that's why these characteristics are different. They have variable oxygen states. You can see each scandium, we have plus 3 state, plus 2 state, and plus 1 state. So like that, manganese can have up to 7 oxygen states. So they have variable oxygen states. As they contain unpaired electrons, they are colored. As they have unpaired electrons, they are paramagnetic properties. As they provide clean surface for adsorption, they can use as catalyst. And mixture of the metals is nothing but alloys. They can form easily alloys, and formation of interstitial compounds, and formation of complexes. These are the properties of transition elements. So these are the main properties of transition elements. Next, oxygen states. Coming to oxygen states, the oxygen states exhibited by scandium plus 3, common oxygen state. Titanium can exhibit plus 2, plus 3, plus 4. Vanadium can exhibit plus 2, plus 3, plus 4, plus 5 because they have d electrons. So chromium can exhibit 1, 2, 3, 4, 5, 6 oxygen states, whereas manganese can exhibit 2, 3, 4, plus 5, plus 6, and plus 7 oxygen states. Plus 7, why? Because manganese, you can see argon 3d5 4s2, 3d5 4s2. So it can lose 7 electrons. It can lose up to 7 electrons. That's why it will have more. Next, cobalt iron, we have only plus 2, plus 3, plus 4, plus 6, but plus 3 is more stable. Plus 2 and plus 2 are more stable. Plus 4, plus 6 are less stable. Cobalt plus 2, plus 3, plus 4. Because of pairing of electrons, the oxygen states decreases down the group. So nickel +2, +3, and +4. Copper we know only +1, +2. Zinc will exhibit only one oxygen state, that is +2, because only 2 electrons it can lose, but all the D10 electrons it will not lose at all. That's why it is not transition. So these are the transition elements shows variable oxygen states due to participation of Ns and N-1d electrons in bonding. Ns and N-1d electrons in bonding. Next continuation. Oxygen states continuation. You can just see here. Scandium shows +2 and +3 is due to 4s2 and 3d1 electrons. But scandium 3 is more stable than scandium 2. So scandium is more stable in +2 only. Sorry, +3, sorry. +3 is more stable because it has 4s2 and 3d1 electrons. So it can lose all the 3 electrons. Manganese shows +2 to +7 due to 4s2 and 3d5 electrons. This already I discussed. And if it loses 2 electrons, it shows +2. If it loses 7 electrons, it shows +7. So oxygen state of zinc is only +2 because no d electrons are involved because it has 3d10 configuration. So 3d10 configuration, no d electrons are involved. So that's why only one oxygen state will be exhibited by zinc, that is +2 only. And the transit metal ions having stable configuration like D0, D5, D10 are more stable. That is scandium 3, lithium, this is titanium +4, vanadium +5, iron +3, manganese +2, zinc +2 are more stable because they have either D0, D5 or D10 configuration. Let us see now scandium 3. Scandium 3 means 4s2 electrons, 3d0. So 4s0, 3d0. It has inert gas configuration, that is argon. If you remove 3 electrons from scandium, it becomes argon. From titanium also, it becomes argon. From vanadium also 5 electrons, it becomes argon. From zinc, if you remove 2 electrons, it becomes 3d10 configuration. It is more stable, completely filled. So they have either D0, D5, and D10 configuration. So D0, D5, D10 configuration. So for first 2 and 3, they have D0, and this is D5, this is D5, and this is D10 configuration. So this is D5, this is also D5. If you remove 2 electrons from manganese, it becomes D5, and this is D10 configuration. And these are D0s, D0, D0, and D0. Because if you remove 5 electrons, no electrons are present in d orbital, and it have inert gas configuration, that is argon. In aqueous medium, chromium plus is stable due to half-filled T2G shell. What is this T2G shell? We'll discuss this in crystal field splitting energy, CFSC, crystal field splitting energy. This topic we have it in coordination chemistry. So in that case, we'll be knowing it. So that time we'll have this discussion, chromium plus 3. Next continuation, oxygen states. Cobalt plus nickel are stable in complexes. Cobalt plus nickel are stable in complexes. And most common oxygen state is +2 for all 3D series. Highest oxygen state shown by elements of 4D and 5D are, as I told you, lutetium and osmium. They exhibit even +8 oxygen state. The common oxygen states shown by the elements of 3B, scandium, yttrium, lanthanum, and actinium is +3 only, as their divalent compounds are highly unstable. So the common oxygen states will be exhibited by the elements of 3B, that is scandium, yttrium, lanthanum, and actinium. So all these oxygen states are important, and what are the nature of these oxides and all we'll discuss later. Next condition, in lower oxygen state, very, very important. This point is very, very important. In lower oxygen state, transition elements form ionic compounds. Means, for example, I'll tell you now clearly. Manganese oxide, that is oxygen state of manganese is +2. It is in lower oxygen state. It is ionic in nature, ionic compound, and moreover, it is basic character, basic in nature, because metallic oxides are basic. Whereas if you take Mn2O7, dimanganese heptoxide, oxygen state of manganese is +7. It is mostly covalent in nature, and moreover, it is acidic in nature. So these points, please note down. This is very, very important. Which are the following are acidic, which are the following are basic. So in lower oxygen state, transition elements forms ionic compounds, and in higher oxygen states, their compounds are covalent. Generally, transition metal ions in their lower oxygen state acts as reducing agent because ionic compounds acts as reducing agents. In higher oxygen state, they act as oxidizing agent because covalent compounds are oxidizing agents. So ionic reducing agents, covalent oxidizing agents, oxidizing in nature. So this slide is very, very important. Please note it down. From this points only they can ask questions. So the transition metals in their lower oxidation state forms ionic compounds and in higher oxidation states forms covalent compounds. And generally transition metal ions in their lower oxidation state acts as reducing agents because they form ionic compounds and basic in nature. And in higher oxidation state, they are oxidizing agents and as they are covalent in nature and acidic in nature. Acidic in nature. So all these points are very important. Please note down in your classwork. These points note down in your classwork. Now trends in standard electrode potentials of transition elements. This we'll discuss now. In solution, the stability of the compounds depends upon electrode potential. What is electrode potential? This we have seen in electrochemistry. The potential difference developed by any of the electrode in an electrochemical cell is called electropotential. So the electrode potential value depends upon the enthalpy of sublimation of the metal, the ionization enthalpy and hydration enthalpy. So the what are the factors depending on electrode potential? Enthalpy of sublimation, number one. Number two, ionization enthalpy, and number three, hydration enthalpy. So delta H of the total is called delta H of sublimation, ionization enthalpy, and delta H of hydration, where that is called total energy change. Smaller the value of total energy change for a particular oxygen state in aqueous solution, greater will be the stability of the oxygen state. Very important. Smaller the value of total energy for a particular oxidation state, for a particular oxidation state in its aqueous solution, greater will be the stability of the oxidation state. So based on this concept, we have electrode potential values is given for all the transition metals of 3D, 4D, and 5D series. You can just see. So the electrode potential values of 3D series, you can see here, scandium, titanium, vanadium. Vanadium is negative. So that is reduction potential they are given. That is from M plus 2 to M and M plus 3 to M plus 2. So this is nothing but what? Reduction potential. Reduction potential values. Reduction potential values. By seeing the reduction potential values, you can see easily which is most reducing. So vanadium minus 0.18, chromium minus 0.9, 1.18 manganese, iron, that is in plus 2 to 0. Plus 2 to 0. You can notice here cobalt, nickel, copper, and zinc. So zinc is having minus 0.76. So in this, the strongest reducing agent is manganese because minus 1.18. More negative the electrode reduction potential value, stronger is the reducing nature. So manganese is the highest reducing element in this M plus 2 to M because its value is 1.18. Next we have chromium. Next we have what? Chromium. Nickel, copper is having least. Copper is least because it is positive. And next zinc. So negative, negative, negative. So next M plus 3 to M plus 2, that is one electron reduction potential with one electron change. We can say minus 0.6, 0.41 plus 1.57. So in this case, it is the least reducing. And cobalt is also least reducing. And here, positive value indicates less reduction, least reducing. Transition elements generally have higher electrode potential values except copper, mercury, silver, platinum, and gold. They can replace H from acid. That's why they have they can replace H from acid. So that's why they have higher electrode potential values, except these metals. Copper cannot displace hydrogen. Still, mercury, silver, platinum, gold, they cannot displace hydrogen from the acid. Whereas all other metals can displace hydrogen from the acids. That's why they have highest reduction potential. electrode potential values. Transition elements act as reducing agents, as I told you, M+2 only. The M+2 they act as reducing agents due to high ionization enthalpy, high heat of vaporization or sublimation, and low heat of hydration. The general trend towards less electronegative values of electrode potential is related to the sum of ionization energies 1 and ionization energy 2 values. The electrode potential values of manganese, nickel, and zinc are more negative than expected due to stability of half-filled Mn+2 and complete filled Zn+2 electrons. That's why this is minus 0.76 and this is minus 1.18. Is having highest because they have M+2 ions. They have half filled and completely filled. If you remove 2 electrons from manganese, you can say manganese. What is the configuration? Manganese is argon 3d5 4s2. So if you remove 2 electrons, then it has 3d5 half filled d electrons. Similarly for zinc also 3d10 completely filled d electrons. For nickel also 3d10 completely filled d electrons. So that's why they have highest due to a stability of half filled Mn+2 and complete filled Zn+2. In nickel, the reason is highest enthalpy of hydration. Nickel will not follow this, but due to highest enthalpy of hydration, it has exceptionally electrode values. That is more negative. More negative means more reducing. More negative means what? More reducing. This more reducing, we have discussed it in electrochemistry. So please note down all these points. Next continuation. The electrode potential values of M+3 and M+2 values shows variable trends because the low value of scandium reflects the stability of scandium+3, which has noble gas configuration. Because if you remove 3 electrons from scandium, its configuration becomes 18. So the low value for scandium reflects the stability of scandium+3, which has noble gas configuration. The comparative high value of manganese shows that manganese+2 D5 is stable. The comparatively low value of iron shows the extra stability of Fe+3. So that's why these are the trends of electrode potential. When you discuss questions based on this, it will be more clear for you. Next, continuation. The comparatively low value of V, vanadium, is related to the stability of B+2 half-filled T2G level. And ETK values for redox couple M+3 to M+2 indicates that Mn+3 and CO+3 ions are strong oxidizing agents. Oxidizing agents means they have positive value of reduction potential, positive ETK reduction potential values. If they are positive, they are oxidizing. Oxidizing agents means negative. So here they have negative. The ions titanium+2, vanadium+2, chromium+2 are strong reducing agents and will liberate hydrogen from dilute acid. These are strong reducing agents. These are positive values of ETK represents strong oxidizing agents and the negative values represent strong reducing agents. So if ETK values are negative, ETK of reduction potential is negative, reducing agents. If ETK of reduction potential, that is electrode potential of reduction potential only, I'm telling you, because M+3 to M+2, this is reduction, decrease in oxidation number. So it is, if they are having positive values, then they are considered as oxidizing agents. So these 2 points you have to remember on the whole. Next continuation. Chemical reactivity and ETK values. Transition elements are less reactive due to high ionization energy. They have less reactive due to high ionization energy, high heat of sublimation, and less tendency for hydration of metal ions. So these metals form ionic as well as covalent compounds. In their lower oxygen state, we know in their lower oxygen state, they are ionic. In their lower oxidation state, they are ionic. And in their higher oxygen state, they are covalent. Higher oxidation number, they are covalent in nature. So generally, ionic compounds are formed by the elements in their lower valence state, while covalent compounds are formed by the elements in their higher valence state. Metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1 molarity H plus ions. They can readily oxidize by 1 molarity H plus ions because they are most reactive. So 3D series are having more reactive than 4D and 5D series. Now, how would you account for the increasing oxidizing power in the series VO plus 2 to Cr2O7 and MnO4 minus? So simply you can see the oxygen state of VO plus 2. So the oxygen state of vanadium is, so find the oxygen states. If you find the oxygen state, easily you'll get the answer. So oxygen state of vanadium here is equal to, oxygen state of vanadium is equal to, we can write seriously. So x minus 4 is equal to plus 1. So implies x is equal to plus 3. The oxygen state of vanadium is plus 3. And chromium it is plus 6. And manganese it is plus 7. So as the oxygen state increases, the oxygen power also increases. As the oxygen state increases, the oxidizing power also increases, due to which they have increasing oxidizing power. They are considered as oxidizing agents. They can bring about oxidation, and rather these two are covalent in nature. Covalent in nature. So the answer for this is simply, as the oxygen state increases, oxidizing power increases. So oxygen state of chromium is plus 6 in this and plus 7 in this. You can see here for vanadium, I have shown one. You know how to calculate chromium and manganese. So if you want even that also, that is 2x minus 14 is equal to minus 2 in place of chromium for Cr2O7 2 minus. So we can calculate like this. So 2x is equal to 12. So x is equal to plus 6. Similarly for manganese also, you can calculate x minus 8 is equal to minus 1. So x is equal to plus 7. Next continuation. For the first row transition, the values are, first row transitions, the values are what they are given, electrode potential values. So vanadium minus 1.18, chromium minus 0.18, manganese 1.18, minus 1, minus, and this is plus. Explain the irregularity in the values, because as they have negative values, these are strongly reducing in their lower oxidation states. Hence, they have negative values. That's why they have irregularity. And for copper, it is plus 0.34 because it is strong, it is less reducing when compared to all these things. Next question. The electrode potential values of M plus 2 to M value for copper is positive. What is the possible reason for this? So the possible reason for this is example 3. So this is why the copper is having positive, because it has D10 configuration for dye positive, and it is D9 configuration, sorry. So M plus 2 to M ion is nothing but it is positive because due to low ionization enthalpy and low hydration enthalpy. That's why it is positive. So it is high hydration enthalpy. High hydration enthalpy, low ionization enthalpy, low sublimation enthalpy, and high hydration enthalpy. Due to this, it is positive. Next continuation. How would you account for the irregular variation of ionization enthalpies first and second in the first series of the transition elements due to D0, D5, and D10 electrons? That is completely filled or half filled or half filled. That's why they have irregular ionization enthalpies for most of the elements, whereas they have incomplete. That's why due to these three, that is D5, D0, and D10. For example, scandium plus 3 is D0, and Mn plus 2 it is D5, and Zn plus 2 it is D10. So that's why their ionization enthalpies have irregular variation. Please note it down. Their ionization enthalpies have irregular variation because of D0, D5, D10 configurations. Which is a stronger reducing agent, Cr plus 2 or Fe plus 2? So Cr plus 2, Fe plus 2. Cr plus 2 is stronger reducing agent than Fe plus 2 because chromium, if we take chromium configuration 3d5, 4s1. So after removing Cr plus 2 becomes 3d4, 4s0, whereas iron atomic number is 26. So its configuration is 3d5, sorry, 3d6, 4s2. After removing 2 electrons, it has 6 electrons. So pairing is more when compared to this. This contains unpaired electrons, more unpaired electrons, and this contains less unpaired electrons. So that's why we can say this is 3d6 and 3d4. So that's why it is stronger reducing agent than iron. So based on electron configuration only, we have all the values. Explain why copper ions is not stable in aqueous solutions. Just repeating the question again. Copper ions is not stable because Cu plus only one electron is lost. Copper configuration is what? Copper is 3d10, 3d9, 4s1. But in ground state it goes 3d10. This is actually 3d9, 4s2, but in ground state it goes 3d10, 4s1. And if this electron is removed, it becomes 3d10. 3d10 means stable. Stable means it is less. 3d10 means complete refilled. Complete refilled means what? It is stable. As it is completely filled electrons, after remove one electron, that is Cu plus ion for this I am writing. So it is stable. So it is less not stable in aqueous solution because it is stable, because it has D10 configuration. It has D10 configuration, that's why it is stable. For M plus 2 to M and M plus 3 to M plus 2 system, the IDK values for some metals are as follows. This question is very, very important. Chromium plus 2 to chromium 0.9 minus, chromium plus 3 to chromium plus 2 minus 0.4, minus 1.2 plus 1.5, iron minus 0.4, and Fe plus 3 to Fe plus 2 0.8. Use this data to comment upon the stability of Fe plus 3 in acidic solution as compared to that of chromium plus 3 and chromium Mn plus 3. So the stability of Fe plus 3 in acidic solution when compared to Cr plus 3. Cr plus 3 it is minus 0.4 and Mn plus 3 it is plus 1.5. So Mn plus 3 and stability of Fe plus 3 is more stable in acidic solution because if you remove 3 electrons from Fe plus 3, what is the configuration if you remove 3 electrons? Iron atomic number is 26. So it is argon. So after argon, it has more 8 electrons. So it is 3d6, 4s2. 3d6, 4s2 actual configuration. After removing 3 electrons, that is Fe plus 3 configuration, it has 3d5 configuration. 3d5 because after removing 3 electrons. So 3d5 configuration. So 3d5 is stable. So that's why the stability of Fe plus 3 is more stable when compared to Cr plus 3. Cr plus 3, if you remove, chromium atomic number is 24. So chromium is 3d5, 4s1. So 3d5, 4s1 implies chromium plus 3 means chromium plus 3 becomes how much? It becomes 3d2, 3d3 actually. So it is less stable. Similarly, manganese also the same thing. Manganese plus 3, it is 3d4. Manganese plus 3, it is how much? Manganese plus 3, it is 3d4. So that's why it is less stable. So the stability of Fe plus 3 in acidic solution as compared to that of chromium and manganese is because of half filled and 3d4 actually. Manganese is 3d4. because of half-filled deconfiguration. Half-filled deconfiguration. Half-filled deconfiguration. That is why it is more stable. So please note down. Next question. So mostly all the questions related to electronic configuration. So it's very important to remember the atomic numbers from scandium to zinc especially. The ease with which iron can be oxidized as compared to similar process for either chromium or manganese metal because of complete half-filled d orbitals, it can be easily oxidized when compared to chromium or manganese metal. Because of half-filled or complete filled, it can be good oxidizing agent. It can be easily oxidized. Next continuation. So with this, I'm ending this session. So in the next session, we'll discuss more about D and F block elements. So please practice what we have discussed so far. Thank you all.